So this is the second type under the substitution method. So we call this is the homogeneous differential equation. Homogeneous differential equations. So in differential equations, there are two meanings for homogeneous differential equations. So there are two meanings. Two meanings in differential equations. So this is the one type, and then we can talk about another homogeneous differential equation later in the next chapter actually. So let's talk about the definition. So what's the definition? A differential equation, that can be written as the y prime, the derivative, as a function of y over x. So if you can write the first derivative as a function of y over x, you call it is a homogeneous differential equation. So it's called a homogeneous differential equation. Homogeneous differential equation. Homogeneous. So we can learn why we say homogeneous. So like a same type basically. So why the same type? So before we do that, let's try to understand how to figure out whether they are homogeneous, and also we're going to talk about another definition later in the section in this lecture, like another definition to for the homogeneous equation. Okay, because if you read another book, they might see that definition there, so you want to understand they are the same thing. But this is much easier what we're trying to do. Okay, so let's do an example now. So so check whether the following differential equations are, say, following are homogeneous, in short. Okay, following are homogeneous. So let's say the first one, y prime equal x plus y over x plus y over x, and this is kind of easy because you can see that you can rewrite this equation as, so if you divide by x both we can write 1 over y over x, 1 plus y over x, and then so you can see this is a function of y over x. Okay. So this is a function of y over x, good. So let's do another one, b. How about this one, y prime equal x squared minus y squared over xy. So if you see this one, so what we can do with this, so you can see again, if you divide by xy, so you can write this one as x squared over xy minus y squared over xy. And then what's going to happen in the first one, 1x get cancelled, so you can write this one as y x over y, and here one of the y get cancelled, you can write this one as y over x. Now the first one, if you divide the top and bottom by x, you can write this one as 1 over y over x minus y over x. So you can see that, yes, so it is a function of y over x alone. How about this one, x squared y prime equal 3x squared plus y. X squared y prime equal 3x squared plus y, and you can see that so first you can divide both sides by x squared, so it is 3x squared plus y over x squared, and if you rewrite this as two fractions, so you're gonna get 3 plus and then this is y over x squared. Since y x squared, there's no way you can write this one as, so what only way you can do is you can pull 1 over x and then you can have y over x, but you can see that it is not just a function of y over x, there's a x sitting there. So that means because of that, this is not a homogeneous equation. This is not a homogeneous equation. Okay, so these two, yes, they are homogeneous. And then what you notice is, you can see that if you look at the numerator and the denominator, you can see that each term has the exact same degree. For example, in the top, all the terms have degree 1 in the first one. In the second one, you can see all of the terms have degree 2. So this is degree 2, and this one is degree 2, and this one is a mixed degree. If you look at the mixed degree, it is degree 2. And but here what's going to happen, you can see this is degree 2, and then but this is degree 1. So that creates the problem. So that means homogeneous means they have the exact same degree in the numerator and the denominator. So let's do one more. Let's say the fourth one as actually not the fourth, d. So it is, let's say x3 d y in 3 y cube minus x y squared dx. So when you have an equation in this form, this is what we normally call the differential form. So instead of you writing as a fraction like dy by dx, what they do, they multiply by dx and write it like that. So this is what we normally call the differential form of the differential equation. Differential form. If you have taken calc 3, you know more about this one, the differential form. When you see like dy dx alone, like that, we call this is the differential form. Okay, so if you see a problem in a differential form, you need to bring it back to the dy by dx version. So you can rewrite this one as dy by dx equal so what is dy by dx? So you can see that this is x3 so you can write this one as, if you bring the other side, so it is 3 y cube minus x y squared divided by x3. So that's the same equation, but you write as in differential form. Now we can do the same thing as before. So you can write this one as 3. So if you divide the top and bottom, and then if you collect the if you divide by x3, so you're gonna get y over x to the cube in the first term, and then minus, if you do the same one, next one, what will happen, one of the x get cancelled, so and then you're gonna have y over x squared. So you can see that, so it is a function of y over x only. See, it's a function of y over x only. So yes, so that means this is also a homogeneous equation. So this is also a homogeneous equation. So now so let's see how to solve these kind of differential equation. So let's talk about that. How to solve them. So there's a special way to solve these kind of homogeneous differential equation. We're gonna make a special substitution. So I'm gonna write the steps. So the first step is we can substitute. So substitute special substitution, what we call y equal vx substitution. Okay, y equal vx, or this one also you can write as v equal y over x. It's the same thing. So that is the substitution we're going to use. So we're going to use y equal vx substitution, or v equal yx. It's the same thing, remember one of them. That's the first step. We're going to substitute y equal vx. The second step, what we're going to do, we can take the derivative. Okay, so let's take the derivative. So once you take the derivative, taking derivative, if you take the derivative, this is a product, so you're going to use the product rule. So we have y equal vx, so it's a product. So if you take the product rule, we're going to say y prime equal vx prime plus x v prime. So that means x prime is 1, so what will happen, v, so this can be v plus, so this can be v plus v prime x. So that means this is always the case, because this is the same substitution we're going to use for all of the homogeneous equation. So that means this we can remember as a formula. So what we have, so y prime, wherever you see y prime, we're going to substitute v plus v prime x always. Okay, v plus v prime x, v plus v prime x, and then we're going to substitute that to the differential equation. Once you substitute this to the differential equation, what will happen, your differential equation become a separable differential equation. So the third step, substitute to the differential equation. Okay, substitute to, I'm going to call this differential equation star. This kind of differential equation I'm going to call this star. So that's the kind of differential equation that you can write as a function of y over x. So this is what we call the homogeneous equation. Okay, so I'm going to refer this. So let's go back. So we can say substitute to star to rewrite it as a separable equation. It's become a separable equation once you do that, as a separable equation. And step, solve for v. Now solve for v first, and then we can say then use y equal vx to solve for y. So it just simply multiply by x. That's how we do. Just multiply by x. Once you multiply by x, you get the y. Okay, so these are the steps to solve a homogeneous equation. So it's the exact same substitution always. So the substitution is y equal vx or v equal y of x, and then once you take the derivative, you always get y prime equal v plus v prime x, and then what you're going to do, you're going to substitute those two to the differential equation. Once you substitute this to a differential equation, your differential equation becomes a separable differential equation, and then you're going to solve the separable differential equation first for v, and then after you get v, what you can do, you're going to multiply by x to get y. So those are the 4 steps to solve a homogeneous equation. So let's look at several examples now. So I'm going to start with something easy first. So let's do this one. So example number 1, solve, let's say y prime equal x plus y over x along with y1 equal 1. Okay, so the answer, and you can see that the numerator and denominator have the exact same degree. Each term have the exact same degree, which is degree 1. So that means you should be able to write this as a function of y over x. So let's see whether that's the case. So we have y prime, which is x plus y over x. Now when you divide by x, top and bottom, so you're going to get 1 plus y over x. Now you can see this is a function of y over x. So let y equal vx. Then we have y prime equal v plus v prime x. You can write it like that because this is a fact now. This is not prime. So so this is v prime. Now what we can do, we're going to substitute. Substituting, we're going to get so we have y prime equal 1 plus y over x. So y prime is simply equals to v plus v prime x, 1 plus, what is y of x? Y of x is equals to v. Okay, so now after we substitute to the derivative, and also for wherever you see y of x, you can substitute v. Wherever you see y of x, you can substitute v. Okay, and then wherever you see the derivative y prime, you can substitute v plus v prime x. Now just simple algebra, you can see that the v get cancelled, so that means it's going to make much simpler now. That term, not always, but here that happen. So you get cancelled, so that means you're going to get v prime x equal 1 simply. So if you write this as using derivatives, you can write this one as dv over dx, v d over x, dv over dx times x equal 1, and you can see that this is separable. This is separable differential equation. So so let's separate and integrate. So we can write this one as dv equal 1 over x dx. So if you integrate two sides, this is easy. So you're going to get v equal this is ln x plus c. Now what we can do, we can substitute for v, but we know that v equal y of x, and once you substitute that, so you can say so let's finish that. So you can say since v equal y of x, so we're gonna have y of x equal ln x plus c. Now if you multiply both sides by x, you're going to get y equal x ln x plus c. Good. Now what is, so that's the general solution, but what we need is we are given the initial condition, so let's use that. So using the initial condition, using y1 equal 1, we have 1 equal 1 ln 1 plus c, but we know that the ln 1 equals 0, so that means you're going to get this equal to c, so that means c equal 1. So c equal 1. So therefore y equal x ln x plus 1. So that is the solution to the initial value problem. So you can see that this is not a difficult problem, but there are certain steps to remember. Okay, so let's do maybe one more problem. Yeah. So let's do another one. So example number 2. So solve the initial value problem. X squared y prime equal y squared xy along with y1 equal 1. So the answer, so you can see that there's x squared on this side. So what we can do, we can divide both sides by x squared first. So that means you can write this one as a y prime equal y squared plus xy over x squared, and then you can divide by x squared both terms. You can write this one as y over x whole thing squared, plus in the second term one of the x get cancelled, so you're going to get y over x. Good. Now what we can do, we can let v equal y over x then we have y equal vx and y prime equal v plus v prime x always. Now what we're going to substitute that into the differential equation. Okay, so let's substitute that to both sides. Then substituting, so if you substitute, you're going to get v plus v prime x equal v squared plus v. Now you can see that as before, in this example also this get cancelled, so that's a good sign. That's going to make it simple. So let's continue now. So after that we're going to get v prime x equal v squared. Now you can see that this is a separable equation. Okay, so so let's separate them and integrate. So we can separate the variables. So it's a dv over v squared equal 1 over x dx. You can write it like that, and then you integrate two sides. Once you integrate two sides, you're going to get negative 1 over v equal ln x plus c. What we can do is we can multiply by negative and upside down, so we can see that v equal negative 1 over ln x plus c. So you flip it over and multiply by negative sign. Okay, so we solve for v, so that's good. Now what we can do, we can solve for y, so we can use the substitution. So since v equal y over x, we have y over x equal negative 1 over ln x plus c. So in other words, y equal, if you multiply by x, negative x over ln x plus c. Now we're going to say use y1 equal 1 to obtain 1 equal negative 1 over ln 1 plus c, but we know that ln 1 equals 0, so that means this is simply negative 1 over c. To get that equal to 1, this says that c equal negative 1. Okay, so c equal negative 1, and then we're going to plug in that and we get the answer. So we can do that here. So we have, if we plug in negative 1, we're going to get y equal negative x over ln x negative 1. So there are too many negative signs here. So what we can do is we can multiply by the negative top and bottom, and then we can write this one as x over 1 minus ln x. So what we normally try to do is we try to write your final answer using the least number of negative signs, because in the top one there are 2 negative signs, but in the bottom one there are only 1 negative sign. So that's one of the things that we normally do. We can write the solution using least number of negative signs. Okay, so we try to be more optimistic, not many negatives. Okay, so some more positives. So you try to write your solution using least number of negative signs. Okay, so that's the solution to the IVP. Okay, so you can say this is the solution to the initial value problem. Okay, so let's do one more. So you can see that it's not difficult, but there are certain things that you have to remember. So example number 3. So let's do a little tricky one. I put a star here because this will be a little complicated. Okay, solve. Let's say x squared minus y squared dy plus 3x squared plus 2xy dx equals 0. So this is given in differential form. So if it is given in differential form, what is the first step to do? You can write this one as as a fraction, as dy by dx form. So let's do that. So in this case you can see that you can take the term to the other side and then divide. So you're gonna get dy by dx is 3x squared plus 2xy over y squared minus x squared. Okay, because there's a sign change, there's a negative sign. Just to cancel the negative sign, you have to switch the term. So that's why x squared minus y squared becomes y squared minus x squared. Okay, now what we can do, we can divide the divide each term by x squared. So divide each term by x squared. Once you do that, you get 3. If you divide this term by x squared, you're going to get 2y over x. I'm going to isolate that term. So we divide by x squared, that means this can be y over x whole thing squared. If you divide by x squared, this can be 1. So what I did, I divide the top and bottom by x squared. Each term, divide each term by x squared. Then you're going to get this. Now, we're going to substitute. You can see it's a function of y over x only. So let v equal y over x and y prime equal, we know that it is v plus v prime x. So substitute. So we have on this side v plus v prime x. On the other side we have 3 plus 2v over v squared minus 1. Okay, unfortunately this time you can see that there are no cancellation of v. So what we do, we're gonna move the v to the other side. Okay, but you can still so what you want to do is you're going to solve this one for v. Okay, solve for v. That's how I'm do. So what we're going to do, I'm going to isolate this term. I'm going to move that term to the other side. So it is 3 plus 2v over v squared minus 1 minus v. Take the common denominator. So once you take the common denominator, so what's going to happen? 3 plus 2v minus v squared minus 1. Take the common denominator and simplify. Once you simplify, what will happen? You're going to get negative v cube, and then we have plus 3v plus 3 over v squared minus 1. Okay, and then so on this side we have v squared v. So now you can see that this is just separable. Okay, so this is separable. It's a separable equation. So that means we can take the v terms one side, x terms the other side, because this is simply dv over dx times x. So let's move the terms around. So we're going to say v squared minus 1 over negative v cube plus 3v plus 3 dv equal, here we have 1 over x dx. So you can integrate the two sides. On this side simple, it is simply ln x plus c. But what about the other side? What about the other side? So in the other side, I know it's like if you get a problem like that, what you normally need to do is you need to factor the bottom and then try to get the factors and write the partial fraction decomposition, and then using the partial fraction you can do it. But this problem is not that difficult, because you can see if you take the derivative of the bottom function, you can see that you're going to get negative 3v squared plus 3. But if you look at the numerator, only the negative 3 factor is missing. but that you can do, you can multiply and divide by that. So that's exactly what we do. So this problem is not that bad, okay, but in general you have to use a partial fraction method to do a problem like that, partial fraction method. So it's a good time to review partial fraction method before you handle like question like that, because there's a pretty good chance that you end up with using the partial fraction method. Okay, so let's continue, let's finish the rest. So we can write this equation as 1/3. We can divide and multiply by -3. So -3v squared plus 3 over -v3 plus 3v plus 3 dv equal ln x plus c. So now remember there was a formula in the four formula method. In the 4 formula method there's a formula we write as f prime x over fx dx. If you see f prime x or fx dx, this is simply natural log fx plus c. So we can use that formula here. So if you forget that, please review the 4 formulas method, 4 formulas. Okay, so it is in the review section, 4 formulas. Good. So using that formula we can write this one as -1/3 natural log of -v3 plus 3v plus 3. The reason is the top is the derivative of the bottom function, that's why we can do that. Okay, so this is equal to ln x plus c. Now what we can do is we can multiply by -3 both sides. So if you do that, you're going to get ln -v3 plus 3v plus 3. You can -3 ln x -3c. So this is ln, this is going to bring as a power inside, so it's going to x to the -3 -3c. Now what we do, we can write this using exponential form. So that means -3 plus 3v plus 3 is the plus or minus the exponential of ln x to the -3 -3c. So you know that using the same trick that we used several times, you can rewrite this one as c, but e ln x e to the ln x3, and then what you can do is, you know that this can cancel out, so that means you end up getting cx -3. Okay, good. Now we're going to use, so since y equal vx or v equal yx, since v equal y of x, we can substitute. So we can say negative y of x cube plus 3 y over x plus 3 equal cx -3. Now what we can do, we're going to multiply both sides by a negative x cube. Once you multiply by negative x cube, you're going to get y3 -3 y x squared plus and the negative, this is negative 3x cube equal c. So this is the solution, but solution because you can see that it's impossible to solve for y, it's difficult to solve for y cube. You can do that using the cubic formula, but that's going to be difficult, so we can leave it like that. Okay, so this is the implicit solution. So this is the implicit solution, to the differential equation. Okay, this is implicit solution, it's not an explicit solution. this is an implicit solution, but that's okay. Okay, you can leave implicit solutions for certain problems like that. Okay, so I'm going to give you one problem for you to try, but this is not that difficult. So the problem is, so it's exercise, I think this is the exercise 1. So why don't you try this one? Solve x squared plus y squared dx plus x squared minus xy dy equals 0. Okay, so you can see the solution in the description. Good. I want to give you like a little note. There's another definition for the homogeneous equation. Let's talk about that because this can help you later. So another definition, definition. So we say if a function f has the property f tx ty equal, if you replace x and y with tx ty, you're gonna get t to the alpha f the original function. So if this happen for some alpha, then we say that f is a homogeneous equation. Then f is said to be homogeneous function of degree alpha. Said to be homogeneous function of degree alpha. Okay, degree alpha. So now, so let's say for example f x y equal x3 minus 2y squared is homogeneous function of degree 3, homogeneous function of degree 3 since f tx ty equal tx cube minus, actually this is not y squared, so I made this is y cube. Okay, y cube, and so then you're gonna get ty cube, and you can see that you're gonna say t cube out. Once you take t cube out as a factor, you get x3 minus 2y3, but that's the original function, so this is going to be t cube the function fxy. So that means according to the definition that this is a homogeneous function of degree 3. Okay, so you can say whereas fxy equal x3 minus 2y cube plus 1 is not. So you can see this is not homogeneous because of that term 1. Okay, because you cannot take the factor. Okay, now let's write the definition. A first order differential equation, first order differential equation in differential form, m xy dx plus n xy, the two functions dy equals 0 is said to be homogeneous. It's homogeneous if both m and n are homogeneous of the same degree, are homogeneous of the same degree. Okay, so this is like another definition for checking whether the differential equation is homogeneous, because if you read another book you might see this definition. So that's the reason why I gave you this one, just to make it easy for you to avoid confusion. Okay, so so this is the end of the discussion of how to solve homogeneous differential equations.